Hello students, in this video we'll construct the Weingarten matrix. Let's consider a surface with first fundamental form E du squared plus 2f du dv plus g dv squared. In second fundamental form, L du squared plus 2m du dv plus n dv squared, and construct the matrix first fundamental form inverse, second fundamental form, which is going to be what? This is going to be a symmetric matrix over here, so this is going to be the inverse of E, F, F, G, hit with L, M, M, N, like this. And so this, of course, is going to be 1 over EG minus F squared, and then G, E, negative F, hit with L, M, 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 L, M, N, which is going to be the matrix GL minus FM, and then GM minus FN, and then EM minus FL, and then EN minus FM, all divided by EG minus F squared. Okay? So this matrix, of course, I know that the eigenvalues of this matrix are exactly the principal curvatures of the surface at a given point, okay? And so I'm very interested in knowing what the eigenvalues of this matrix are, but I want to relate it actually to a different operator. So let me do that. So now consider, let n hat be the unit normal vector. Then I know that the derivative of n with respect to u is a combination of Ru and Rv, where R is the parameterization of the surface, because that's a line in the tangent space, and Rv and u and v is some numbers Cru plus drv. In other words, n hat u and n hat v lie in the tangent plane, so I can write them as combinations of Ru and Rv. Okay. Now we also know properties of the second fundamental form. I know, for example, that L is equal to negative of n hat u dot Ru. I know that M is negative n hat u dot Rv, which is also negative n v dot Ru. And finally, N I know to be what? N I know to be negative n hat v dot Rv. Okay? So I'm going to use these relationships over here to find some equations I can solve, right? So let me take equation 1, and I can do two things. I can dot equation 1, so I can do 1 dot Ru is going to give me what? If I do 1 dot Ru, I'm going to have a negative L is equal to what? Negative L is equal to A, and then Ru dot Ru is E, so it's going to be an AE plus BF, okay? I can do 2, I can do 1 dot RV, so let's do 1 dot RV. 1 dot RV is going to give me what? It's going to give me, if I dot 1 with RV, that's going to give me a negative M is equal to what? Is equal to AF, that's an AF, and then plus what? And then plus B times G, okay? Now I have two equations and two unknowns, so I can use Cramer's rule, right? So Cramer's rule tells me what? Cramer's rule tells me that A is going to be what? A is going to be the determinant of negative L, negative M, and then BG, FG, over the determinant of A of E, F, G by Cramer's rule. So this is going to be what? This is going to be LG minus FM, negative LG plus FM over what? Over EG minus F squared. That's what A is. Now look at A over here. A is the opposite of this entry over here, right? So that's the opposite of A, okay? That's one thing to consider. let's look at the next one. Let's look at what will B be. So B is going to be the determinant of, now I keep the coefficients of B fixed, so I have an E and then an F, and then a negative L and then negative M over the same determinant, over EG minus F squared, right? So this is going to be what? This is going to be an FL over here, FL positive, and then minus EM over EG minus F squared, okay? Good. Notice that that term over here is this term with a negative sign, right? So both those terms are the same except for a negative sign. Now what we're going to do is this. So now let's look at equation 2. Let's look at 2 dot NU. 2 dot, I wanted to hit 2 with RU, not NU. So let's hit 2 with RU. 2RU is going to be what? If I do RU with this thing, that's going to be negative M. Negative M is equal to, negative M is equal to, if this was an RU, that's going to be a C times E, and then a D times F. Okay? And if I do 2 dot RV, that will be a negative N, right? Negative N is equal to C times F plus D times G. Okay, excellent. Again, we have 2 equations, 2 unknowns over here, so let's solve these equations. So let's solve these equations over here, 2 equations, 2 unknowns. What are we going to see? We'll have that the coefficient C is going to be the determinant of what? The determinant of negative M and then negative N. And then I'm going to keep the C's, I'm solving for C, so I change those, and I leave these the same, so I'm going to have an F and then a G. Over what determinant? Over the determinant of the coefficient matrix, which is EG minus F squared. Beautiful. And what will this simplify to? This is going to simplify to an FN positive, minus GM over EG minus F squared. Lo and behold, that is the opposite. That's the negative of this entry over here. And let's do D last. Let's do D. What will D be? D is going to be the determinant of what? It's going to be the determinant of, I leave these the same, so I have an E and then an F. And then finally, those coefficients F and G are going to turn to a negative M and a negative N over the determinant of EG minus F squared. And that's going to give me what? That's going to give me a FM positive, right? And then a minus EN negative over EG minus F squared, right? Okay, and that's of course the opposite of this thing over here, right? So in other words, this matrix over here, I'm going to write this matrix over here as what? So that's really my A, that's my B, right? So that's my B is really this thing over here with the negative sign. So our conclusion is the following. Our conclusion is that 1 inverse 2 is the opposite of this matrix. I have an A over here. That's A. Let's look over there, make sure that's A. That's LG minus FM, good. Now the B is EM minus FL, so the B goes down over here. And then what? The C goes over here, and then the D goes over here, right? And so this matrix over here, this coefficient matrix is called the Weingarten Matrix. So this is the Weingarten Matrix. It's really the what? It's really the transpose of the coefficients of the differential of the normal vector. So sometimes you see this written as W is equal to negative the differential or the Jacobian matrix of the Gauss map or the normal map. So this is really sometimes really negative G like this. Now, of course, as always with the problems in differential geometry, there's always this issue of signs. So sometimes whenever I teach a multivariable calculus class, I say, if you do the Stokes theorem problem or the Gauss theorem problem or you do this orientation problem, for some reason you parameterize the surface incorrectly and you get a negative with the answer I get, I'm not going to penalize you because you showed a different parameterization. You weren't sort of careful enough with the choice of, in a speed environment, in an environment where you're going really fast doing parameterizations and calculations, I'm not so worried about the fact that you didn't check it in or out, right? That's sort of a more elementary thing, like clockwise, anti-clockwise. There's always these issues with negative signs. Nonetheless, the Weingarten matrix is really the negative differential of the Gauss map or the differential of the normal vector, right? So it's really the Jacobian transformation of the normal vector written in these bases with respect to what basis? With respect to the bases RU and RV for the tangent space of the surface at that point. Thank you very much.